revolutionizing 3D printed robot parts. Now the first thing I want to ask is how many people here already developed their own 3D printed parts for the robot? Raise your hand. Okay, how many people would like to? Okay, good, we got a good mix here. Now 3D printing, and this is maybe an old term for it, but it's a disruptive technology. It means it's something brand new, something revolutionary that we didn't really have before. Actually, it has been around for a while. I've been doing this for 25 years. But back then, it really wasn't the same kind of thing. You know, it wasn't as accessible, it wasn't as easy. Things didn't come out all that well, but it has been around for a while. And one of the first questions you should have if you're thinking about a 3D printed part is one, can I buy it off the shelf? I mean, there's a lot that goes into designing your own part. You have to CAD it up, you have to print it, you may have to reiterate it and a few things like that. But can you just buy it? A lot of times that's a whole lot easier. There may be some lead times involved, but if you could just buy it, that's really something you should do. In industry, I made a lot of automation equipment, and the first thing I would do is I would buy as much as I could off the shelf and then put it all together with some custom parts like 3D printing. That worked out pretty well. I know that's how a lot of people make the robots, and that's good. But also, can you make this part out of the appropriate material? It may be you really need for it to be metal or some really high temperature engineering plastic that you just don't have. So you have to take stock of the resources you have, work with that. Do I need just a few parts? Sometimes if you have to buy them, it's expensive. You know, you get something from some long run thing, you want 10,000 parts or something, but that is a good place where 3D printing comes in. You can just make one part, and it's cheap that way. And does it need to be custom made? That's the real beauty of 3D printing is you can make it for exactly what you want. 3D printing should be used to solve your problems, whether at home or on your robot. And it should also be used to solve things that you never really thought of. Like in industry, we used to make a lot of equipment. And it had to be safe, so you had to have machine guards. And as a robot inspector, I look for this too. I see something like that in your robot, and that's a pinch point. Your team could be hurt by this, people in the field. So with 3D printing, it's easy enough to just make a quick guard like this. And it's good practice too. But it's really simple, it's lightweight, cheap, and it does the job. And I know I've developed things like this before. I came up with this part for circuit breakers because I got tired of a robot being reset, just being touched or something like that. And as a robot inspector, we always make sure that your main circuit breaker is accessible so that people in the field can find it if your robot's on fire, which you don't want. So this yellow color comes in, or this orange color comes in handy. And not only that, but it's got that round radius part on the top. So you can just jam your finger in there. You don't even have to look. You just jam your finger in there. You can turn your robot off in a hurry whenever you want. And so what 3D printing allowed me to do is take standard part that everybody uses, and you can download this from our website too if you want. Please don't print it in black, and it'll last you forever, and it really gets the job done. Like I said, circuit breaker can be hard to find. This allows it to be with the color. The switch is missed because it's that tiny little red thing. And it prevents, because that switch is below the level, it prevents it for your robot from being reset by a field piece or anything like that. A lot of people had that happen with coral dropping into their robot. And anybody that had one of these never had that problem. But that's a classic example of using 3D printing to solve your problems. And I know on this robot, I had somebody counting for there was over 150 3D printed parts on there. It fixed a lot of problems and saved us some money in the process. And it's not just decorative ones like this, that just cover things up. It's also functional ones like these rollers on here. They're crown rollers and work with flat web belts. We didn't have to buy these. We just could make whatever sizes and spacing that we wanted. And even in cases like this, you look at this and you say, well, I need this part to be made out of metal, because it's thin, it'll bend and flex. You don't want that. Especially this outer one. Those are both aluminum. That's a good choice for that part. CNC easily. They both have to be catted, so. But there's a little spacer. That's an easy one there. And even these gears here, they're herringbone gears. Plastics like this have natural lubricity, so you don't have to oil them. The problem with oil, like on chains and things like that, is it attracts dirt and junk. You don't have to do that with plastic gears. And if you just make them, they're breaking, you can just make them wider. And then there's less force on them. So let's go to some other parts that we might want to do here. There's a belt. What do you think? Is a belt a good choice for 3D printing? It can be done. I've seen it. It's a terrible choice though, because belts tend to be fiber reinforced internally. They're very highly engineered, and 3D printing isn't a good application for that. But this spacers and things like that, great application, and end plugs and things like that. They may be just for decorative uses, but you'd do this if you were in your profession, you were designing a product, you would do something just like that. Now you look at this part, chain and a sprocket. You obviously wouldn't make the chain out of it. I've actually seen people do that. It probably lasts about 2 seconds for them. It's just not a good application for 3D printing, even with some of these expensive engineering materials. Neither would this be. That's a steel chain. That sprocket there is also steel. If you tried to 3D print that, which you could, if you didn't break it right away, you'd wear it pretty quickly. So that's not a good choice for 3D printing. This particular piece here, this was used it just folds over and lifts the robot off the ground. That one right there, that's made out of polycarbonate. It's a very, very tough piece of plastic, molded in one piece. You couldn't really 3D print that. Thin parts aren't very good 3D printed, and it would not hold up at all. And again, this material is cheap. Most of you have CNCs. You have to CAD it anyway, so you just do it that way. One thing you have to be careful with on sheet plastics and 3D printed parts is don't have a fastener, a mechanical fastener like this, that is putting too much stress on your part. You see how there's a big fender washer on there? That holds it in and keeps it from getting cracking, radiating out for that hole. That's one thing you should be looking out for. Sometimes people even put a rubber washer in there. Holds it in tightly and really, really spreads out the force on it. Here's another good application for 3D printing. These are for sponsor panels. But the sponsor panels, they have special internal parts there that wires and other stuff go inside there. It's not structural, custom made. Works great there. Good choice for it. Both of them on there. Now, today we're going to be talking about fused deposition modeling. That's actually a trademark term. Sometimes you'll see fused filament fabrication. There's other kinds of courses, you know. A lot of people talk about resin printing. I wouldn't use that right now. I mean, it's getting better all the time, but there's multiple steps. There's toxic materials and things like that. It's just not worth your time. And of course, when with high school teams and things like that, we don't want them getting near any toxic materials. But it's pretty straightforward. And the engineering on these is just moving at a lightning pace. It's just amazing what they've been doing. If you haven't looked at it up close, 3D printing, fused deposition modeling looks a lot like this. You can see the gaps in between there as it laid down. That's one of the reasons why you have to understand that it's not the same as if you had an injection molded piece. It's not as strong because in injection molding, everything is working together. Here, there's gaps in there. And you have to be careful of that. You kind of see it up close there. That's a little more like it. There's some overlap. And if you have under extrusion in your parts, and we'll look at some of those later, you'll have less of this, so they're less strong. So you have to design your parts well, and you also have to print them well. Let's get into some consideration for the machines and the filament. I got a brief statement about home printers. A lot of you have some ones you've had for a long time, some maker bots, Enders, Elagoos, all kinds of stuff like that. I hear a lot of people say, yeah, I spent a couple hours working on this, tweaking it and everything like that for an hour of printing or something like that. It's just not worth it. They have machines now, and they're cheaper. Like Bamboo has a Black Friday thing coming up. I just can't believe the prices they sell these for, because I've used some of those older ones I talked about, and they're just the biggest pain ever. But some of the newer ones, they work so much better. Spend your time designing and making parts, not fooling around with your 3D printer. And don't spend a whole lot of time messing around with a lot of materials. If you're a more advanced person, you can do this. There's a lot of high-level engineering stuff. Well, you're not going to use Ultem and stuff like that. We don't have the high-temperature printers for that. But there's polycarbonate, nylon. There's some carbon-filled things that are really useful. But start out and just like bring it down to 2, because then you're very knowledgeable about how those materials work on your machines. Some of the ones are a lot more engineered these days. They've done a lot of chemistry into them to make them better. For instance, 5 years ago, you wouldn't use PLA, which is terrible material. It was brittle for the most part. It printed really well. But you don't want your robot necessarily to look good. You want it to work well. You want it to be reliable. These days, PLA, you'll see it PLA Plus, PLA Tough, PLA Modified, usually with acrylics and things like that. It's so much better than it used to be. And it still prints pretty well. And another one I'd like to suggest is TPU. It's rubber, basically. And it comes in a couple of different hardnesses and things like this. Mostly, if you look on the Shore A, what you'll get is 95 Shore A. And it feels kind of hard, which is good, because then you can have a part that holds its shape, but it can take a heck of a beating. You can take TPU parts and hit them with hammers, and they'll just kind of bounce back. I mean, the inner layer bonding is so great, and there are so many times where this is really something that can save you on your robot. You just need to start working with it so you have it in your mind, you know its characteristics. And you can even start getting into things like, back in the day I used mostly commercial machines. They would have multiple heads. I've got one now. It's a Bamboo H2D. It actually has 2 heads. I can put whatever I want in either one of those heads. And you can use the characteristics of different materials, for instance, to make a part a certain way. Something to think about. You don't have to run out and buy one of those. There's plenty of other ones you can work with now. But like I said, it's something to think about on your robot. The only statement I would have, though, and I got this directly from the Underwriters Labs people. They did a study on these 2 materials, ABS and ASA. ASA is kind of a new one. But they said that the problem with these is there's a lot of styrene fumes that are released. People should not be around these. I used ABS in my lab a lot, but that's because I had, we had a lot of air turns in there, and there was evacuators for that. So there it wasn't a problem, but here you've got this thing sitting in your bedroom, or sometimes it's a shared space with that. Just don't use it. There's plenty of other materials than ABS or ASA. One thing that's really important on your robot is understanding the forces that are acting on your part. That will help you design and 3D print this part much better if you understand what's going on. A lot of you are familiar with, the static forces on them, and you can easily calculate that. And you can say, well, I'll just look at some material that, has high tensile strength or something like that. But that's not usually what gets you. I mean, there's static forces, of course, and sometimes there's a cyclic forces. You might know it better as vibration. But the one that really gets you is that impact force. You see how it's a sudden spike? It's almost impossible to calculate. I mean, that's why you'll add in a safety factor. But when you run your robot into a wall or something like that, somebody hits your intake, that's when you get that impact force, and that's what breaks your parts. So you have to keep that in mind. Because they always tend to break at the worst time, and you don't have a spare. It's really kind of a heartbreaking thing. Now, this is from some testing that this mechanical engineer did. And this shows the great difference between the impact strength. Remember that I talked to you about that impact force? You can see these different materials. PLA is way down here, isn't it? That G's down there too. People think that's a miracle thing. If you want to use something like that, I would suggest its cousin, PCTG. It has a lot of qualities that are better. And one of the things they did was they took these two chemistries. They said, we're going to add more ones that'll give it resilience, and that's going to be our PCTG. And that one has, as you can see, much better impact strength. You probably wouldn't notice the difference when you made your part, but if somebody ran in your robot, that's probably when you would. But you can see at the top, PC is polycarbonate. You need an advanced machine to make one of those. It has to be enclosed, it has to be heated and everything like that. But it actually prints pretty well. I made a couple of replacement parts for some PLA ones that were broken, and it was pretty easy, although there's a lot of cases down below that you can see there's TPU. Because it's a rubber, it's extremely impact resistant. That particular one has carbon fiber in it. Don't get the idea that adding carbon fiber to any material makes it better. All it does is it makes it stiffer. And it's not the same carbon fiber. For instance, when Boeing makes a composite airplane wing that's carbon fiber, they use specially engineered, it's either mats that are made of woven carbon fiber or long strand carbon fiber. That's way different. The ones that you get in your filaments are very, very short. And in reality, while they make it stiffer, they can actually make it weaker because there's those bonds between the plastic and the fibers, which can be glass fibers, Kevlar fibers, or carbon fibers is the most common. But it pretty much makes it stiffer without really adding anything to it. So that being a carbon fiber filled TPU, it's actually doing pretty well. It would probably be at the top if we just plain carbon fiber. I use a lot of these materials. I rarely use carbon fiber. The only time I would if it was a thing with thin walls that was, a big piece, and I wanted it to not warp or anything like that. That's one of the things that carbon fiber does. It prevents your thin walled part from warping. So it has its uses. You just have to know what they are. And in case you're wondering, in industry, we use a test like this. Pretty simple. You just put something in there and you see it's got a notch in there. And a known weight hits it in a known space with a specimen of a known size. That's what testing's all about. And it breaks it. And from something like that, that's where those impact tests came from. So it's a legit test, although it's of a sample. It's not of your part. Your part may be slightly different. Keep that in mind. Design considerations. One thing you need to know about this, if you remember from the cross-section of 3D printed parts, it has a lot to do with the interlayer bonding in certain directions. Now, what we're looking at here is an anisotropic part. That means its characteristics are different in different directions. For instance, if you look on the left, forces are put on this, and its strength depends on the interlayer bonds. If you have it oriented this way, force depends on the tensile strength of the individual fibers. You have to break those. You see how they don't break cleanly? And we'll see later how that makes a difference. That's important when slicing, too. Remember the loads? All right. Now, I talked about impact forces before. Tensile strength is different. That's just pulling a sample apart. Look what's up there. Look where PLA is. It's pretty strong, isn't it? Well, look, Polycarbonate is right up there with it. This one was in yellow because this was an article about PCTG, and all the graphs are highlighting that. That's why that's in yellow. Interestingly enough, again, it's at least as strong, if not better, than PETG that a lot of people like to use. That's pretty common. PCTG is not very common. It's a little bit more expensive. But if you're into discovering these things, try a spool when I do some tests on it, see how it works out for you. You know what the other piece of equipment was like, the impact tester. In the industry, this is what we use. It's a tensile, called the tensile tester. We have a lot of these at 3M. They're at least $400,000. So they're kind of out of the reach, but we use those in the automotive and aerospace industry because our customers require, great precision in all the measurements and strengths and everything that we're claiming, and it has to be repeatable. The only way you can do that effectively in industry is to use an equipment like this. But we're in the maker world. We don't have that kind of cash. We do with what we have. So the internet has a lot of cranks on it. It also has a lot of great information. You have to be able to sort this out. So one of my go-to places is a guy called Stefan Hermann. He's in Germany. He speaks English, don't worry. He is a mechanical engineer, and he has a site called CNC Kitchen. And he used to be in industry, and he did this kind of on the side, but now he does this full-time. So he's really getting into it. The thing is, he is a trained engineer, and he is also a knowledgeable 3D printing enthusiast. So he combines the two, and his tests and everything he does are very informative. And he kind of walks through them, how it works. This is his version of a tensile tester. Looks kind of janky, but it gets the job done. It even has a computer printout, as you can see here. So what Stefan does is he says, I want to be able to test the filament. I'm not just taking the manufacturer's specifications. I want to make an actual part, and I want to test it and get data from it so I know what changes I make in printing or changes in filament make a difference to me. Here's this sample right there. You see how it's kind of a weird looking hook thing? And this is fixed at the bottom of his machine. And then this moves up on those lead screws you can see there. So this is what he's done. He says, I'm going to print two different kinds of samples. One is printed in the z-axis, as you can see on the left. The other one is printed on the xy axis, as you can see there. And you can kind of see what we're getting after here. Here, when he pulls it, we're going to be testing the interlayer bonding. And this one is going to be the tensile strength of the filaments in there. So he puts it in his machine, and this is what he gets. The first sample, as you can see, was printed in the z-axis. You can see how it broke. Nice and smooth. There's no tearing there or anything like that. There, this part was ripped apart. He used the full tensile strength of those fibers, and they didn't go down without a fight. You can see what it looks like there. But the important thing is, okay, we did these tests, but what's the data from it? I want to see the data. And here it is. Now you can see what this basically means is the ones he printed in the z-axis, where he's pulling the inner layers apart, look how much less force it took them to pull those apart than it did where it was along the axis of the filament. So if you're designing your part, you should orient it so that you're using this strength, not this one. This is the same filament. I can't remember what it was, but it doesn't matter. Every filament will be like this. Well, there's some that have better interlayer strength. Like I mentioned, one of the reasons you want to use TPU is that stuff does not like to come apart. The interlayers there, and polycarbonates and nylon is kind of the same way, but most of the other ones are like this. So orientation is extremely important. So So what that means is, say you're designing this L block, this is how you want to do it. Like this, because if you're pushing on it, you just push the filaments apart, whereas here they maybe bend a little or something like that. Of course, it's got some problems with this part. Notice the square corner down there. You don't want to do that. And if you're sending a part out to a machinist, you never have square internal parts. Oh, you have a question there?
Would wood be anisotropic, depending on if you go on the grain or against it?
That's a good question. Wood is anisotropic. Like if you took a 2x4 and you tried to bend it or something like that, it's very difficult. But imagine how, think of a log. In order to cut it across to cut a tree down, there's a lot of chopping and sawing and cutting and stuff like that. But if you want to split it, you just take an axe and hit it on the end, boom, comes right apart. So that's anisotropic too. All right, let's look at a real world part here. Okay, this is a key rack. This could be a coat rack too. Keys, who cares? They just hardly weigh anything. They work there. But what if it was a coat rack? You know, I'm talking about a middle January Minnesota parka kind of jacket. You know, you've got half your junk in your pockets and everything like that. It's a lot of weight. So if you make this part like this, it'd be easy to print it that way, wouldn't it? You can see the layer lines on there. And you can just see what's coming here. The strength is inner layer there. It's just not going to work. And you could say, okay, I'll print it on edge like this. Yeah, you know, that'll work. But you remember how long that thing was. And you got to have all these supports in there. And, you know, you're limited, machines are limited in height. Maybe you want this one, it's not going to work out. So, what could we do to modify this part's design to make it better? You could start going to something like this. Because if you do, and I used to do this a lot, because I had application equipment that went into automotive facilities, and believe me, those guys are rough on their tools. I had one where they, on a Ford F-150, and they'd apply the 3M products. They would literally be about 30 feet away, and they'd throw it back into a huge barrel, you know, because they had to gather some other stuff. And you got to remember, they're working on trucks that are moving past them. They do not stop. So they are rough on that, and parts like that would just snap right off. But I did this very commonly. I'd have holes in there, and I'd use bolts for other things like that. You can get plastic screws. McMaster is a great source for this. They have very coarse threads on them, sort of like drywall screw, but drywall screws are brittle, and their shank isn't very thick. These would have, they'd be much coarser than this, but they're really simple to use. I use them in place even of inserts because they can be removed and replaced a lot. But use the materials that are appropriate. In this case, metal. Yes?
Wouldn't it have like a weaker, like, wouldn't it break easier if you were pulling it on this way?
You mean out like this?
Like let's say you accidentally snagged on your coat, wouldn't it break?
No, because the bolt that you have there also keeps it from pulling apart. You know, you've got the layers like this, and it'll probably come off, but the bolt will maintain it there. You know, if you have some long dangly thing that's coming out, you could put a bolt in there, but it gets to a certain length, it's really hard to do. Just replace it with a piece of aluminum rod or something like that. Like again, you have to know the appropriate material for what you're doing. Yes?
For something like this, would you be 3D printing the threads, or would you be like tapping into the 3D printed part?
A lot of times you can just put a hole in there. And remember, 3D printers don't always make them round. So always, if it's a precise hole, make it smaller and drill it out. But a lot of cases, you just make it a certain size, and you don't really want to tap in there. Like I said, you can use actual plastic screws and things like that. Put them right in there. It's a very simple thing to do. This is another example. It's a little bit longer, but you can see where they put something out there. And of course, the threads are better in metal. A lot of times you'll want fine threads, but in plastics, soft materials, wood and things like that, you have big, thick, coarse threads, because they hold on to the material better. And they go out further, you know, the difference between the depth here isn't nearly as much as a fine thread, so you don't want that. Machine bolts aren't really good in plastics. That's why I said, they make special screws for plastics. Again, use the appropriate thing for your parts. But, if this doesn't work out for you, if you want to do something different, let's take another look at this and do this. Now you see how those parts are inserted. It's really the same thing. You've got a coat racket thing there like that, but the parts are printed separate. You can make a nice long piece here, flat, looks great. You have these holes in there. I probably wouldn't make square ones because they're hard to enlarge and stuff like that. And you have to be more precise with your fits. That's a whole different thing, is fits between parts. But this way, it's printed like this, so it's not using the inner layers, it's using its tensile force. Yes?
You said you probably wouldn't use squares. What would be your recommendation?
Oh, try to make a round hole if at all possible. All right. There's also a lot of CAD-related things that you got to think about before you even get to printing. We kind of talked about this before. A part like this, square inside corners, you can just imagine, you know, what's going to happen there. You put that fixed on the bottom, you put a force up there. What's it going to do? It's going to break. You see that? Very common. The fix is really simple. You can do this in CAD. Just put a radius in there. It's amazing the difference that it makes. And the reason for something like this is, imagine these red lines are lines of force, lines of stress going through there. You see how in square corners and things like that, they're concentrated? So the force per unit area skyrockets in those square areas, and that's why they break. Some of you might have the opportunity to use finite element analysis. And what finite element analysis does is it gives you a predicted forces on your part. And it says, well, it'll give you a scale, and they usually use false colors in there to show you that, you know, red and stuff like that. That's where the forces are high. And you can see exactly what you'd expect. The very highest forces are right there in the corner where it's likely to break. If you went ahead and put that fillet in there, you can see how the lines of force are really straightened out there. They're not concentrated as they were before. So, this part started out as just an angle with this thread boss in here. And these people did a couple of things to make it much, much stronger. This is without changing filaments or anything like that. To be honest, the layout that you do and the CAD work you can do will have much more of an impact on your final part than picking some fancy filament. Question?
So it's like you're trying to minimize at all points, minimize the rate of change in stress on the object?
Well, it's the amount of stress. I mean, rate of stress comes in if I'm talking about the impact, but it's all about stress concentrations. That's the most important part. So to make this part, as it is now, ideal, here's what they did. They started out with a radius, so that wasn't just a 90-degree corner there. Then they added this plate in there to connect it to both sides there, much stronger. They had this in there. It's just hanging out there by itself, you know, and that's going to snap off in a heartbeat. Probably do it as you're screwing something into it. So what they did was they added some flanges on both sides, and they connected it to the wall, so it's supported all the way up. This is a much better part now. They could have put some fillets in here, but this is just so much stronger as it is. Now look what somebody did here. They made a part because the connection to the broom handle snapped off. It was probably made out of plastic too, but they did the right things here. You see how they added flanges there? You got one there, small one there, and those are on both sides. It makes that part just so much stronger. They could have done some things better. Instead of, this is something you use in wood or metal. You should use, something where you just drill a straight hole through there, not a countersunk one like that. They took away a little strength by using that, but you know how a broom works. You're twisting this around. It's really, the part is really a problem there. So, did a pretty good job. Yes?
I also see that they rounded the edge instead of having it as a square, like you said would be better before.
Right. So they did most of the things right there. Like I said, they just could have put the screws in just really flat. Yes?
I'm forgetting how to words, but so as compared to right angle edge curving it, is any amount of that better than or
Oh yeah.
Sorry.
Yeah, make it feel. Putting a fillet in there, yeah. Even a small amount.
Like the more you do that, I assume the better it gets because it feels like how
Yeah,
much
you do, but then there's kind of the law of diminishing returns. All of a sudden it gets big and heavy and stuff like that. So, and any amount really makes a huge difference. Let's get into some slicer choices.
Just
here.
if I take 5 minutes to go.
Okay. So anyway, you guys are all familiar with these terms. Because people always say, well, what infill should I use? There's a lot of them. A lot of them are actually decorative. And this one's pretty standard, right up there. But there's some other ones that, because the thing about that, it's anisotropic. It's strong this direction, you'll crush it this one. You don't want that for your parts. There's better choices here. Like this one here, cubic, that's pretty good. But there are some other ones here. Look at that one over there. 3D honeycomb and gyroid. I prefer 3D honeycomb, some people like gyroid. There's still much better choices if you're talking about infill. The density, you'd be surprised how little difference that makes. I mean, you're not going with 0, but you don't need to go, anything really above 60 is kind of, again, it's the law of diminishing returns. The most important thing is the wall layers. Like see this part? That one has infill in it, and this one they up the wall count. So this is going to be much stronger than that one with the infill, isn't it? Yeah.
Let's say for whatever reason I want it to be 100%. Is there any difference between any of the modes if I wanted to do that?
No, it's just 100%. There's almost no reason to do that. Like I said, above 60, there's just really no returns. Walls are important though. Sometimes they're called shells, sometimes they're called profiles, it depends on what it is. I mean, you can just imagine something like this. It has a few walls. It's going to wear, it's going to snap. Those are the parts that are going to wear. So when you're thinking about this is like a default part, 2 walls, 50% infill. And that's good for prototypes when you're doing fit and finish, but in an actual part, you're going to want something more like this, especially the walls. And remember that if you have holes in the middle, the walls are increased there too. So if you're putting a screw through there, some people do tap them, and you're going to need extra space in there. It just makes it so much stronger, and it connects it to the outer walls too, if you have parts on the inside. You can see there. And that can make a difference. See, this is to drive a belt. You see the tooth pattern on there? Somebody made this. It's got 4 shells on it. Not bad. We usually would go with 6. But this hex has to drive this, and it has to drive through this. The infill. Somebody left it at 15%. So you can see that right there. It's very thin, and that's going to drive through that. So guess what happens? That's what happened. It lasted for a while, but then this was on an intake, and it jammed, and then boom. That impact force went through the roof, took out that infill, and this is what happened. They reprinted this later with a much thicker infill, and it was great. Never had a problem with it after that. But just be careful. You're looking out for, look at this is all these gaps and stuff like that, under extrusion. You have to be careful for that. I even look sometimes while it's mid-printing just to see. Some people made some parts here that tried to improve on. You can see they added thicker walls and stuff like that. It's a really oddly sloppy job. It's very well under extruded. But they made a chance out of it, and they made some improvements, but they missed some details there, yeah.
How would you fix under extrusion?
That's something in your slicer. You can go in and change that variable. Anyway, so if you want to contact me, yeah.
Post 3D printing, if you have something like a soldering iron or a 3D printing pen, you're able to touch up those areas.
Yeah,
and
you
help
can do
fix
that.
them up.
I've used it for that before. But usually you just want to remake the part, yeah.
Would you recommend using 3D printing for like pulleys for belts and things like that?
Oh, sure, you've used them. But you got to remember, if you're using a skinny little pulley or a little belt, you're putting a lot of force on there. So if you know you're going to be using 3D printed sprockets for that, just buy a little bit wider belt. It'll distribute the force better, yeah.
What are your opinion on supports? Tree supports, regular, or custom resin for FDMs?
Oh, these tree supports these days work a lot better. They're a lot easier to pop out and everything like that. So it looks like they're going to kick us out here. But if you guys have any questions, feel free to contact me at this address.